This is TAU Unbound, the English language podcast of Tel Aviv University. Please welcome your host, Ido Aharoni, Tel Aviv University's graduate, member of the Board of Governors, lecturer, writer, and veteran diplomat.
Welcome to yet another episode of TAU Unbound. I'm Ido Aharoni, your host, and today it is my distinct pleasure to host Professor Ehud Gazit.
Thank you so much.
Welcome to our podcast, and such a pleasure to have you. I mean, you have such an impressive bio. I mean, I have to read at least one paragraph because it's so impressive. So, Ehud Gazit is an Israeli biochemist, biophysicist, and nanotechnologist. We'll talk a lot about nano, try to understand what it is. He is a professor and endowed chair at Tel Aviv University and a member of the executive board of the university since 2017. In 2015, he was knighted by the Italian Republic for services to science and society. How many people do you know that were knighted by the Italian Republic?
I didn't bring my sword with me.
Yeah, where is the sword? Exactly. And he was recently elected as the 2023 International Solvay Chair in Chemistry, which is a very lucrative appointment, a position that was previously held by 15 of the top world scientists, including 3 Nobel laureates. He's also a member of the Israeli National Council for Research and Development, and this was an appointment by the Israeli president. And from 2012 to 2014, he served as the chief scientist of the Israeli Ministry of Science and Technology. I will add to that, I mean, there's an endless list of achievements here. Let me just add to that he also served as the chairman of the technology transfer company of Tel Aviv University called Ramot, which is responsible for some of the biggest success stories of Israeli tech sector. And if I may also brag a little bit about Tel Aviv University, it's the number one university outside of the United States when you look at the integration between
startup started by the university graduates.
Yes. So welcome.
Thank you so much.
I
it's
must
a pleasure
say,
to be here.
You're a young man. How did you accomplish all those
I'm not so young.
So,
working hard.
So before we started this recording, we chatted a little bit about your upbringing, and you said you grew up in Rishon LeZion, and which is south of Tel Aviv, a major city south of Tel Aviv. So tell us a little bit about your upbringing and how you ended up developing such an interest in science.
So I always knew that I like science. Science is something that I think I'm biased, but I think that it's the most wonderful profession that a person could have. Quite from young age, I was involved in all kinds of things that are related to nature. I was part of the Israeli conservation movement, חברה להגנת הטבע, as a youngest, and I always liked biology. However, I was in my high school, I learned physics, mathematics, computer science as I was expected. But only after my army service, I felt brave enough also to go into biology, which I like a lot.
And in the army, I should tell our listeners and our viewers, you were an infantry combat soldier. You were not
paratrooper.
You were not a scientist.
I wasn't a scientist. I was a paratrooper. Yes.
And so you were able in your scientific work to bring together biology, chemistry, physics, and I'm sure to you it sounds only natural. But tell us a little bit about why is it so important to approach this from an interdisciplinary perspective?
Okay. As you rightly say, we are really in the interface between biology, chemistry, physics, material science, because we are dealing with the most fundamental events in nature. So we are looking, you said nanotechnology. Maybe not all the listeners are familiar with nanotechnology. This is dealing with the most fundamental interactions in nature, the formation of structures by very simple building blocks. And we study, for those not coming from scientific background, I'm always telling that we are dealing with sociology of molecules. We're trying to understand how molecules bind to each other, why two would form a structure, why the third one will not be part of it, how you can disintegrate this structure.
Now, if I understand correctly, you're interested in solid materials, right?
We are, yes, you're right. So you can come to biology. Indeed, sometimes I say that we are dealing with solid state biology.
All right.
As you may know, solid state physics is the basis for all we know in modern electronics, telecommunication, modern computers, even the cell phone that we use. It's all solid state physics. That's transistors and other things.
And nanotechnology is the process that allows us to dive as deeper as possible.
Into these dimensions. But very clever engineers were able to make all these devices. Evolution, or God, were even smarter because they were able to make even more sophisticated structures from such building blocks. So all the things that we know in modern electronics, we have in even the most simple bacterial cell. You have sensors, motors, integrating units, everything in a very simple cell. So this is where things converge. God is a wonderful nanotechnologist. We are able to make most advanced structures that currently no engineer could make. So this is where things come together. We're interested in the most fundamental processes in life or in nature, and there how it goes to different directions. So it could be related to formation of functional structures in animals, plants, human beings. It could be related to the development of materials with unique properties, building something very light in weight but as
durable,
rigid as steel, have things that have unique optical properties.
So basically what you're saying, and hopefully I got it, I'm correct in my rephrasing of what you're saying. When you reach that the deepest level of the fundamentals of the solid material, you're in a position to redesign it in such a way that will give it new properties. For example, durability, longevity. So for example, if today an airplane can, we build an airplane for 50 years, then in the future, using nanotechnology, you'll be able to develop a material that will last thousands of years.
Or it could be able to heal itself, which today it's only part of the biological world.
So, for example, no corrosion.
No corrosion, being able to correct cracks that are being formed in the structure.
Now, is this only theoretical, or
it's very practical.
It's very practical.
We are experimentalists, although we are using also computational methods. I don't want to get too much technical, but we are using what is known as quantum chemical theory. We understand the full behavior of the material on the quantum level.
So when you say that you're using quantum computing, you mean that you're using extremely powerful computers to make the calculations?
No, not quantum computing, but rather quantum methods.
Methods, okay.
It's meaning, I don't want to get too much into the physics, but as some of the listeners know, is the Schrödinger equation to know the behavior of simple, very, very simple molecules. Nowadays, using methods such as DFT, people got several Nobel Prizes for this, we can estimate the electronic behavior of much more complicated
materials. If you can give us two examples, one of work that you're doing currently in the lab, and second, of a possible application in the future, of once it becomes practical. Right now it's only experimental, but once it will become practical, if you can give us an example of application, applied nanotechnology.
Okay. So I'll give two examples. One more from the material science point of view, and the other from biomedical applications. So from material science point of view, we are working on piezoelectric material. What does it mean, piezoelectric? Piezoelectric is a material in which you apply a force, you get electric current. Most of piezoelectric materials, and quite a lot of them, are based on toxic metals, mainly lead, but also others. We're able, by understanding, designing, as you rightly understood, understanding the behavior of the solid state arrangement of biomolecules, to have structures that are as potent as those toxic lead-based, environmentally unfriendly piezoelectric materials. And we have very nice publications as well as patents. What is it good for? Think about a situation in which you can harvest energy from the human body with those elements that produce electrical current based on just movement, for example, of your heart, of other parts of your diaphragm, other parts of your body. And we are looking for a situation in which we'll have medical devices, safe, bio-friendly, could be implanted in the human body, that will give energy to different medical devices that we need. For example, in the case of pacemakers, as you may know, some individuals need to have pacemakers, and one of the issues is the battery. And you have another surgery to take it out, and with all the risk that they have. If you can get the energy from just physical movement of your body, it would be remarkable. People always give this example of the football player who was he crashed on the during a match. Then at the age of 20-something, he got a pacemaker to make sure that his heart beats correctly. And during his life, he will probably have to go through 5 or 6 different surgeries to replace the battery. So this is one direction. This is materials and their application in biology.
And by the way, the idea of movement as a rechargeable function can influence a whole, different range of products and services.
So
and
energy harvesting is something that we're really interested in, and we are very much involved, engaged in this process.
So our viewers and listeners, the term is energy harvesting.
Energy harvesting.
That's the term, energy harvesting. So the movement itself generates energy, and so you don't need a battery.
Yeah, we have a lot of energy around us and inside us, but we are not harvesting it as well as we would like to.
So this is one example.
This is one example. This is how we take advantage of the understanding how biological molecules arrange to form structures with advantage properties for our benefit. However, I make another level of complexity. Sometimes structures are related to disease. For example, when you have neurodegenerative disorders, let's say Alzheimer's disease or Parkinson's disease, you get a formation of solid materials. I will use the term that you already were referring to, in your brain. So, in parallel, my group is developing therapeutic compounds, drugs, to treat neurodegenerative disorders. We already have compounds in clinical trials. On the other hand, we make structures for energy harvesting, as well as making structures that are actively optically, studying diseases that are related to young age. How we do all of this? This is because we deal with the most fundamental properties, and then it's diverged to all these different fields. So if I can convince the audience is the fact that if you are dealing with the most I'm using fundamental many times, but the most fundamental events in nature, you can understand different disciplines, and this is what we do.
Now, what is the smallest particle that we know that we're able to identify in nature?
Well, it's there's the atom, different atoms, and of course the subatomic particles, the neutron, proton,
nanotechnology,
electron. But nanotechnology usually
is in the molecular level.
In the molecular level, however, I will use your question to say that we can even manipulate things that are smaller than the atom.
Smaller than the atom.
This is a patent that we have in a nice publication, collaboration with my good friend Rona Aman from the Weizmann Institute and Yossi Paltiel from the Hebrew University. So it's a multi-institute collaboration because it's a very important subject. We are making things that are related to spintronics. Are you familiar with this term?
I'm eager to learn.
Okay. So we're speaking about
spintronics,
subatomic particles. One of them, which all of us know, is the electron. The electron, this is what quantum mechanics teach us. It could have two kinds of spins. What's something that is called as spin up and spin down. It's not sure that this is the real physical meaning, but could have two quantum states. What we can do with our ability to make these solid structures that have unique organization in themselves, we can have a beam of electrons. The beam of electrons, they have a random distribution of spin down and spin ups. And we could do what we call spin filtering. We can get only spins in one direction. You would ask me what it is good for. And spintronics, many people see it as the new state of electronics. Because all the devices that we use, all the technology that is used now to record us, to have this delivered to the viewers, it is based on electronics. What is electronics? You turn on and off a transistor. So you have electron or you don't have an electron.
It's a binary state.
It's a binary state, yet it's a binary state that is actually quite costly. If you notice, most of your electronic devices, they produce quite a lot of heat. Your computer, your telephone. Think about a situation in which you have not two states, 0 and 1. You have 3 states. Up, down, and no. So, immediately you get 3 times the amount. And think about a situation in which the energy cost to make it on and off, in our case up and down, is only a small fraction of the energy needed to turn things on and off. So spintronics is another thing of the future. So we are dealing even with the subatomic.
So I must ask you, because this is
and
also.
I should say that it's really a beautiful. I really like collaborations, and this is collaboration of leading scientists in leading institute in Israel. Although we are in Tel Aviv University, we have other outstanding universities in Israel.
Of course.
And this is something that I'm very proud of.
And by the way,
we already have a spin transistor made. With this.
Yes, and of course we in this podcast we highlight the fact that the strength of Israeli higher learning institutions is that they're very collaborative.
Yes.
And but I must ask you, you're talking about things that sound to many of us as science fiction. What kind of equipment you need to be able to do all the things that you're describing?
Well, we are using equipment that may sound very advanced, but it's reasonable. We are using a lot of electron microscopy. Again, for the viewers who are not familiar, it's a microscope that instead of using particles of light photons, it uses electrons. However, we know electron microscope from the middle of the 20th century. We published a very highly cited science paper with an electron microscope that was built in the 80s. Other than that, we are using quite a lot of spectroscopy. This is the ability to understand the electronic state, vibration, interaction of different structures. We're using spectrometry. This is a way that you test the size of molecules. So there are some people who are experts in a certain technique. However, our approach is to take advantage of all we have around in order to ask the big questions. And this is what we do. But we use, and if there's more advanced techniques now, there's imaging mass spectrometry. It's quite interesting when we are using it, but we are users of technology. We are not inventors of technology. And this allows us, you ask how can we do all the things? It allows us to understand all these systems using all the tools that are at our disposal.
Now, you are the chairman of Ramot, which is the tech transfer company of Tel Aviv U, which is responsible for many of the success stories of Israeli tech sector. What do you think needs to happen in order for all those scientific breakthroughs, as you described, with spintronics and so on, to become more commercial?
This is a huge question. You read my biography, but as part of it, I was involved also in leading institutes in the world. For example, MIT, as well as Cambridge University. And what I see when I compare Israel to these, let's say, Cambridge, Massachusetts, and Cambridge, UK, is the fact that innovation is not inferior. Actually, I think it's superior in many terms. We Israelis, many times, are thinking out of the box. I have a small story about it. When I was at MIT, I decided that I will take advantage of this elite institute, and I took a course on thinking out of the box. And then I realized that Israelis, we need the course of thinking inside the box, because we are always thinking outside of the box.
Need to tame the Israelis. The Israelis need to be tamed.
So we have the innovation. As you said, we are very good in Tel Aviv University. Now I will be the Tel Aviv University ambassador. We are extremely good in making new companies. However, it is much more difficult to do it here in terms of capital, in terms of being exposed to the large funding agency and investment firms. But if you go to Candle Square, Cambridge, Massachusetts, and you look at many of the companies, Israelis are leading, or at least a very significant part. So what I think, and I'm a very optimistic person, I think that now, and I know that many of the viewers are outside of Israel. Israel is a huge opportunity for investment. We have here really the most advanced technology in the world. And you have the opportunity to invest in something with a very good value for the money for those who are coming in. So I think that we need more capital. We need more access to large organization. But, I won't be modest here. We're able to do things, and now I'm speaking both about Ramot, if you think about technologies that are related to disk on key, as well as others, and also personally, we're able to bring pharma technology all the way to clinical trials, something that would, as you know, it's a very expensive business. It's tens of millions of dollars to get something to phase 2 clinical trials, and then hundreds of millions of dollars to phase 3. And we're able to do it in a very cost-effective way. So I think there's a huge opportunity here, but we lack, as I said twice before, we lack capital, and we lack some exposure to the entire ecosystem of the investing community.
So you're part of a community that is really on the cutting edge of science and technology. What you're saying is that you need capital, you need strategic partnerships. And what is in the most optimal view, how much time do you think will take for humanity to take all those scientific ideas that you were able to prove and experiment in your lab and turn them into really applicable technologies in real life? What is the time frame here?
Well, it depends on the technology. If you're thinking about material science, this would be quite fast. You could have it within, fast in technology development terms, in years, but low number of single digit of years. Things that are more related to biomedical devices, it may take longer, several years. And pharma products, this is the thing that takes the longest. But on the other hand, this is the big thing that could change the fate of Israel economy.
And could change the well-being of humanity.
Of humanities. You were getting into the technology transfer, of course.
Yeah,
I think
because it can change medicine.
You can change medicine. I think us as Israelis, we always have the example of Copaxone from the Weizmann Institute, in which it took 30 years from the initial experiments until the approval of the drugs in the end of the 90s. So the work was done in the 60s by Michael Sella, passed away recently, but for me, a mentor and a role model. And only in 98, it was approved for use. So think about it, 30 years. But this is the technology that actually made Teva to what we know today. Hopefully we'll get back to
By the way, do you see any
billions
change?
of dollars of sales?
Yeah, of course. Copaxone and Teva is a wonderful example. Do you see any change in the regulatory environment post-COVID?
COVID would change things, but the regulatory bodies are conservative, and there's also a good thing about it. For me, as a person who developed therapeutic compounds, drugs, I might like it to be more relaxed, but I think that the standards are still kept still being kept at a good level. I think that they were correct during the COVID time because it was such a unique situation in which you need to relax somehow the regulation. But I have to see the holistic picture, and I think drug development is a very, very serious business. You have to be very careful, and I think the bodies have the good balance between these. Maybe things were slightly relaxed after COVID, but not it wasn't a revolution, rather an evolution.
Right. No, I was thinking about the fast track to approve the vaccine, and I thought maybe it did change the mindset of some people. But I'm glad to hear from you that you still see the regulator is maintaining a healthy balance.
I think the balance is healthy.
Now, let me ask you a question, because, to us, the laypersons, people like me and most of the viewers and the listeners, it sounds like you're really engaged in science fiction and that you're already at the new frontier. But I'm sure that there's, even for you, a new frontier. So in the future, what would you like to be doing that you're not doing today?
Well, there are still some mysteries, I think, that we need to unfold. So, again, since we are in this interface between the different worlds, I will mention things related to, first of all, biology, and then to physics. In biology, I think that what we really need to understand to a much deeper is the aging process. We understand aging, but it's like you have this cartoon of blind individuals who are touching an elephant. We see some parts. We don't see the integrated picture of this. So aging is one direction, and since we had a short talk, but you know that I'm interested in so many things, all the things related to superconductors and quantum computing, this is the other thing. And again, I think that also here, biology, chemistry could give some directions that were not explored yet.
So on aging, would you say, and this is for our viewers and our listeners, would you say that the first step is to look at aging not as an inevitable process, but rather than as a disease? And if aging is a disease, at least theoretically, a cure can be found. Would you say that?
Well, I wouldn't say a disease, but rather a process that we don't fully understand, that maybe could be reversed, that maybe could be stopped. I don't see a priori any reason that aging could not be manipulated. I would say, put it lightly.
Yes, and I think that this is a wonderful statement, a very optimistic statement.
Yes. And I think that we understand more and more, and, I'm biased, but I think that the secret to understand aging is related, once again, I will say it for the fifth or sixth time, the most fundamental events not in nature, but in every cell, which is this organization of various molecules to form structures that are related to aging. They are associated with aging. There are some events, lipofuscin. This is, if you would ask a scientist, what is the molecule that is, or structure that is most correlated best with aging? There's something that is known as lipofuscin. I don't have the time to go into the details. But there are structures that are related to aging. Why they are being formed? Are they the reason for aging? Are they the byproduct? Even if they are the byproduct, what can we learn if we go back on the processes that made them and led us to a situation of being old? Why they are cardiovascular diseases are a major issue in modern medicine. As you may know, a zebrafish, you can induce a complete damage to the heart, mimicking a myocardial infarction, heart attack, and the fish just build the heart again within days. How can you do it for us? The secret is in the genes of the zebrafish, which is not so far away from us. There's so much to learn in this domain.
And I'm sure that our audience is as excited as I am to hear all those amazing things that you're working on and the way your mind is thinking of tackling those issues. I wish I had more time, but you have to go, and we have another engagement. And I just wanted to thank you for educating us.
Thank you so much. It's a pleasure.
And really getting us so excited about your work.
Thank you.
And I'd like to invite you again.
Okay.
Maybe in a few months' time to hear about new frontiers and new developments.
Thank you so much.
Thank you. And to our audience back home, until our next episode, goodbye from Tel Aviv.
This is TAU Unbound, the English language podcast of Tel Aviv University. Please welcome your host, Ido Aharoni, Tel Aviv University's graduate, member of the Board of Governors, lecturer, writer, and veteran diplomat.